yeah, so this talk is about seismic imaging, partly from ambient noise and partly from other types of seismic imaging. On the example of the Western Alps. So as usual, it's a very collaborative work that was done with the former PhD students, Yang Lu, Chloé Alder, Dorian Sorgel, Ahmed Nouibat, who is still preparing his PhD, of course, Laurent Stelly, Helle Pedersen, Thomas Baudin, who is in Lyon, Liang Zhao, who is in Beijing, and the two geologists, the real geologists, Marco Maluza from Milano and Stéphane Guillot from ISTerre. And of course, this is work based on a very big database of well, seismic data that was that on temporary experiments that we reran in the whole Alps with the Alpere project. So Alpere working group is also a co-author, and another two experiments by the Cipher Alps team in the Western Alps. So they are also co-authors because they recorded the data basically. So you may know that in fact I was part of the history of these correlations and the emergence of the Rayleigh wave or the green functions from correlations of Coda waves because at that time, so I am the poll of CampiOne poll 2003 in science. Where is the don't know. Ah, okay, here. Is it that one? Yeah. Yeah, it's that one. So this paper was on long-range correlations in the diffuse seismic coda. So I did that work with Michel Campillo, who is, by the way, my neighbor in ISTerre and also a very good friend. So at that time, I was working a lot partly on the propagation of waves in heterogeneous media, but I was also having big seismic experiments on the structure of mountain belts, which is, I don't know, my goal in my life of scientist, to know what's below the surface in mountain belts and how mountain belts are being built. So I was a co-author or first author of these two studies, this first one in Science and this second one with also Ludovic, Michel and so on the that was published in JGR in 2005, and which was the first paper that showed causal and acausal Rayleigh waves in the green functions. But then the work on these correlation of Coda waves and ambient noise was more dedicated to more physics or mathematical proof of that. So, and I am more, as a geophysicist, I'm more geo than physicist. So, well, anyway, I was very happy when Nikolai, Michel, Laurent, and Michael Ritzvoller generated that paper that was in 2005 that showed that you can really extract some information on the subsurface with these techniques of noise correlations. And so this paper was on California, and many of you probably know it. And so these are two group velocity maps, one at 7.5 and one at 15-second periods. And what their conclusions was, and it was using the transportable array of Alperae, so a quite dense 2D seismic array. And they were saying, oh, we are happy because we did find the geological map. And for me, finding the geological map is not something, well, that important. I mean, as geophysicists, we don't want to find the information that the geologists have been knowing for 100 years, but we want to find more. So that was the second point, the first point. And the second point is that at that time, the places where we had this type of arrays were quite rare. Myself, I was working in Iran. You know, it's me here. And at that time, so that was in the early 2000s, working on the deep structure of the Zagros mountain belt, which is here, and it's a mountain belt generated by continental collision between the Arabian plate in the south and the Eurasian plate in the north. But we were installing our stations along sort of linear arrays, which is very bad for imaging and very bad for noise correlations. So we couldn't apply these types of techniques on these types of data. And then I started to think about working in the Alps, not only because Grenoble is in the Alps, but also because for geologists, the Alps is something enormous. Well, this guy who was a professor of geology in Paris and who had very good connections with Grenoble, he said in French something which means that every geologist has two home countries, his own home country and the Alps, which says that the Alps is something very, very important for geologists. And the second one is Émile Argan. Émile Argan was a professor in the University of Neuchâtel in Switzerland. And Émile Argan not really discovered, but he formulated an hypothesis saying that you don't generate mountain belts because the Earth is cooling, and so it's becoming like a dry apple that makes foldings. That was not the origin of mountain belts. The origin of folds that you can see in mountain belts were mainly because of horizontal displacement and not of vertical displacement. So it's something that says there is, well, no real vertical displacements. All the vertical displacements that you see in mountain belts are all generated by horizontal displacement. And this was about the beginning of the 20th century. This was about at the same time that the theory of continental drifting was plate tectonics was sort of discovered. So that was very important. And that's in the Alps. That's the section across the Swiss Alps. Just to say that the Alps, geology has almost been invented in the Alps. So the Alps is something important that, as a geophysicist working in Grenoble, you cannot miss, basically. Okay, so just to give a short overview of where, well, the Alps, as you maybe you all know, is this mountain belt here. So it is in this entire geodynamic setting of the Mediterranean, where you have, and it's due to the collision of Africa with Eurasia, and in particular in the Alps of this very small plate here, which is the Adriatic or Apulia plate that collides with Europe. And by the way, it is so there are plenty of mountain ranges in that regions, and the Alps are the only one where Eurasia underthrusts or subducts beneath Apulia, so toward the south. Okay. Alps is also, and in particular the Western Alps, is also an interesting place because it's the place where continental subduction was discovered. And this discovery happened in this location here. That's Italy. The border. It's a geological map, so it doesn't shows the border, but the border between France and Italy is somewhere here. So a French guy named Christian Chopin, who is a mineralogist, he discovered this mineral, which is a coesite in garnets named pyrops in high-grade blue schist of the Western Alps. And these minerals, what is important with them is first that they originate from continental crust, and they originate by metamorphism of this continental crust buried to 100 kilometers depth, 2.7 gigapascal. So they discovered in that location, so Christian Chopin discovered in that location that continental crust may be buried to as deep as 90 kilometers. This observation implies a complete revision of the current ideas on the relationship between oceanic and continental crust. A subduction process is not necessarily blocked by the collision of continental masses, and continental lithosphere may be subducted as well. And at that time, so when this paper was published in 1984, most geoscientists were thinking that it was impossible to drag continental lithosphere and continental crust to such large depths because of its buoyancy, because it's light with respect to the mantle. So this discovery of coesite grains in garnets from the Dora Maira Massif here in the Piemonte region in Italy was the first mineralogical evidence of the burial of continental crust to these large depths. But what about the geophysicist, in fact? Well, first a model of that, how you explain that. So you start with this history. So in the geodynamic scenario of the evolution of the Western Alps, drawn by geologists. So you first have Europe here in the left, and Apulia or the Adriatic plate, Adria in the right or in the south. So you first have oceanic subduction, so subduction of the oceanic crust toward the south. And then it doesn't stop because the plate continue to converge, and you drag to very large depths part of the continental crust, including these rocks from the Dora Maira. And when you continue so you have oceanic subduction, then continental subduction, then continental collision. You have no more oceanic rocks, which are the blue ones here. They have sort of disappeared or been concentrated on the surface. So you make a real collision between the two continents, and the rocks that were the continental rocks of Europe, of European crust, that were dragged, that were buried to large depths. They sort of they are exhumed. They come up, and they eventually appear at the surface where the geologists can find them. So that's a schematic way to explain this phenomena, having first continental collision and then exhumation that make these rocks appear on the surface. But of course, do we have so that's the image that what they believe the Alps look like now. Which geophysical traces of this geodynamic history can we, as a geophysicist, can find? So this is the Echorscope, this deep seismic reflection profile. That's quite old, at the end of the 80s. So it's a normal incidence seismic profile that was crossing the northwestern Alps. So Genève is here, Grenoble is here, and Torino is here. So this profile was run, and what you see in the bottom is depth profiles of a line drawing. So somebody picked all the reflections at normal incidence. This is active imaging, by the way, with sources, with vibrators and explosives at the surface, and recorded by numerous. It's the oil industry way to find oil, but with much deeper and much longer recording. So that's depth. Here you have 25 kilometers. And it goes from the Massif Central here in the northwest to the Po Plain in the southeast. And what you nicely see is the crust, the continental crust, that goes down, and the limit, the lower limit of this reflective part, because what is mostly reflective in continental lithosphere is the crust, because the mantle is almost homogeneous, the upper mantle. So you have the moho here, so the cross-mantle boundary that dives to about here. And then we have this red stuff, but these were not recorded by normal incidence seismics. They were recorded by another type of seismics, which is named wide angle, which uses the fact that the reflection coefficient at large angle, is stronger than at normal incidence. So these are wide-angle reflections. But if you just forget about these wide-angle reflections that were recorded more to the south and not along the profile, you see that you have no evidence here that on the normal incidence that the moho goes deeper than about 35 or 40 kilometers, and it's basically the reflections basically stop, the deepest one stop very close to Grenoble and not further. Hopefully they had these normal incidence reflections showing the moho, the European moho here, down to a maximum of 55 kilometers, so very far from the 90 or so kilometers that was recorded by mineralogy. So no geophysical trace of the continental subduction in that type of image. So the geologists who are interpreting these images, as you may all know, the geologists are very imaginative. And so they were interpreting these images, and as you can notice, they didn't really bothered about, well, they knew from mineralogy that the crust, the European crust, had been going as deep as maybe 19 kilometers, so they draw it going down. But there is no geological evidence of that. So here it's 65 kilometers, where the maximum here is 55. So they sort of extrapolated the geophysical data quite a lot. And so this was a problem. And Laurent already showed his image. That's from his paper of 2009. So at that time, it was the first trial of tomography of the Alpine region from seismic ambient noise, using these seismic stations, which were already a lot, in red here. But what they got was that. So I remember Michel came in my office and said, look, we are doing something useful for structural seismologists. We found the moho in the Alps. And I told them, well, okay, you have a deep moho where you have high elevations, but we know that since 20 years, maybe. So you have much more than that. So he was very upset. But so I said, well, and maybe it's not yet the time of ambient noise tomography in the Alps. So what can you do to improve that? What you can do is just to have more stations, of course. And what you have here is a movie of the installation of the Alpes seismic network and permanent seismic network from the 1st of February 2015 to mid-2017, I guess, where you see that in those 2 years, the number of seismic stations and the coverage of the sort of greater alpine region has improved a lot with homogeneous coverage. There was no single point in that region that was at less than 30 kilometers from a seismic station and a broadband seismic stations. And we also had these OBSs in the Ligurian Sea, which are a real part of the Alps, or at least in between the Alps, which are there, and the Apennines, which is another mountain range here in Italy. So that's a very big set, a very big data set. And with many laboratories in Europe and many countries participating. So I was the PI of the French part of that. So that's where we got at the end. And the difference between the previous movie and this one is that I added the two Cipher profile in the Western Alps that we installed with Chinese and Italian colleagues here. And also other temporary profile like that was easy, but that was before Alpere, SWASD, which is a very dense experiment funded by the Germans, but the data are not yet open, and other temporary experiment like a small one here. So now. So in between 2012 and 2019, now it's normal like that because many of the stations have been removed. There was really, during these 7 years, a very big lot of data. So data from network Z3, which is the Alpere temporary seismic network, which opened 18 days ago, that everybody can accept. It's now public. The Cipher experiment that we had before Alpere for this one in the south, Cipher and Cipher 2 was at the end of Alpere. So this data set is public, but this one will become public in 1 year from now. And of course, we used a big lot of permanent networks. And I have to acknowledge all the participants in field experiments. And I think you have one here. That's Sven, you probably participated in that. And of course, a big thank you not only to people who run the seismic the permanent stations, the temporary stations, but also to people who distribute and make this data open, which has really changed the world of structural seismologists, having all this data and all this data easily accessible. So before the Alpere, we started working on the Cipher Transect, so that was 2012-2013 across the Western Alps. So Corsica is somewhere here, Nice and Grenoble here. If you don't understand geological maps, that can happen. So the first result, the first thing that we did with this data is receiver functions. So receiver functions, it uses teleseismic earthquakes. So it's passive seismology, but with earthquakes still, because, well, it's linear, so we were going on doing the same things as in Iran. It's also because this type of seismic array with a very high density, about 5 to 7 kilometers between stations, it gives you data and images that you can start to compare with the geological map and show to the geologist. You are about at the same at the same size as well, not yet, but as what the geologists have in terms of geological maps or geological data. So this is the receiver function section. So it's named a common conversion point stack. So it's something very, very basic and which is sensitive. Well, it's conversion of P to S waves at major velocity discontinuities. So you very nicely see the MOHO. The European MOHO as a red block. So you, even if I remove this black line, you will still see it. On the Italian side, it's not the same. It's not as easy because the Po plain, which is an enormous basin with 10 kilometers thick of sediments and all the industry of Italy and a lot of noise and a lot of motorways and so on. So it's a nightmare for seismologists. So the data are usually very bad there, which is what you see here. You don't even see the MOHO that we know is at the depths from other data. So you have the European MOHO and you can trace it, thanks to this spot here, you can trace it to 75 kilometers, which is 20 kilometers better and deeper than on the Ecoscope section. So we said that that was the first seismic evidence of continental subduction in the Western Alps from this tiny spot of data. What we have on top is this blue spot. So it's in red with red means a positive P to S converted wave with respect positive amplitude, same polarity, which corresponds to velocity increasing with depth, and it's blue when the conversion happens on a boundary with velocity decreasing with depth. So you see that here we have this blue that is picked here with this dotted line, and this corresponds to a velocity decrease. It means that on top you have higher velocities than below. On top you have what we name the Ivrea body, because there is this big, this is the Bouguer anomaly along this same cross section. So you have this big Bouguer anomaly high, which means that you have material which is heavy, high density, very close to the surface. Well, we knew that from the early 1960s, that there was this Ivrea body, but what we have here is that beneath the Ivrea body, which is assumed to be a mantle body, drawn in blue here, but beneath it you have low velocities. It means that you have the crust below, because this is the mantle. So to have this type of opposite polarity, negative polarity conversion, you need low velocities below, so you need crust below. So it means that you have the crust of Europe being beneath the mantle of Adria. So we proposed a model that we compared to the gravity data, but only forward modeling. So of course the geologists added geological constraints from maps and model. We modeled the gravity anomaly. We add a few petrophysical constraints, and we got a crustal model of density and P-wave velocity from trial and error forward modeling, and the geologists could draw a first interpreted geological cross-section which shows the continental collision, the continental subduction here. Okay. Then we did everything a structural geologist can do. In particular, in this region, there are quite a few earthquakes, which are drawn here as a purple circle. So we did what is named local aspect tomography. It's travel time, quite simple travel time tomography. So you record the travel time along your array of stations, which is at the surface of all these earthquakes here, plus permanent stations, and you invert the travel times for VP, absolute VPs here from 5 to 8, and also the time difference between S and P arrivals. You invert it for VPVS, but it's slightly less reliable. And you can, here you have the converted, the structures that we got out of the CCP section that I showed you in the previous slide. So European MOHO, the Adriatic MOHO that we got from other data. And you have velocities. You can see the blue. The blue is mantle with P-wave velocity around 8. And yellow, it's about 7. So it's not really mantle peridotites. It's we believe from petrophysical constraints that it's mantles with serpentinites with some somehow hydrated phases in it, serpentinized mantle. And most importantly, we have here below the high velocities, we have lower velocities. So these lower velocities, they explain these negative polarity converted phases. So we could draw a second update or first update of the geological cross-section with slightly different structures, namely here, this vertical boundary. So started to improve the imaging of this part, which is named the subduction wedge. Then came the time of ambient noise tomography, finally. So it was the PhD of Yang Lu from all these stations. So it was only part of the Alpes seismic network plus Cipher, so it was almost 1,300 seismic stations, only Z component, 4 years of seismic data. So as Laurent explained, he did a linearized inversion for group velocity maps and a 1D nonlinear probabilistic inversion for VS. And along the Cipher Alps line, which is still that one, and these are the images that we've seen before. He got that VS image, and I was very disappointed because we were not seeing that part, which is really important because it is the part where you have these European crust going beneath the Adriatic mantle, and he didn't image that. He didn't image the continental subduction. But then the Chinese colleagues, it's Zhao et al. 2020, they took his group velocity data and they applied a Bayesian transdimensional inversion using the methodology by Thomas Baudin and colleagues, and they got a new VS model that shows indeed the low velocity zone beneath the Ivrea body. So that's the Yang Lu's image, and that's Zhao et al. 2020, and which indeed has, we see the European crust, the European low crust, being buried beneath the Adriatic mantle. So you see that, of course, much better than with receiver functions, because you really see the velocities. You see it with your eyes. You have the low VS beneath the high VS. So that was a very important result for them. And for me, I said, okay, so maybe we can extract some interesting information from ambient noise tomography. No, I'm kidding. Michel is going to hate me. Anyway, so of course, as we're always working with geologists in this tab, with this transdimensional inversion of ambient noise tomography data, we had new elements to constrain the geological interpretation. So that was the second or third iteration in the construction of the geological cross-section from all the data I've shown you before, and also from this type of data from petrophysics that give you the P-wave velocity on the horizontal axis as a function of pressure or depth, of course, for different types of petrologies, including serpentinites and eclogites and peridotites and gabbros and blue schist, etc. That are the types of rocks we have in continental collision zones, like here. So you have the VP on top and the VS, and having both of them, VS from ambient noise tomography, VP from local earthquake tomography, they don't have the same resolution, they don't have the same maximum depth, because as you see with local earthquake tomography, you can't go deeper than the depths of hypocenters, basically. So but having VP and VS in this region, we could start drawing, interacting with the geologist, drawing this second update that was published last year. 5 minutes, okay. So one step more forward was the transdimensional inversion for group velocity in the thesis of Ahmet Nuibat. More station, 1540, including the OBSs in the Ligurian Sea. So Laurent already told that, and he could find the continental. The European continents, continental crust, going beneath this crust, with a lot more information of inside the crust, with backthrust and stuff that could be used to draw another geological cross section. But and now I come to the Cipher 2 experiment, which was the most recent one in the Northern Alps. And so this is another CCP image from receiver functions in the Northern Alps. And if you may remember the previous one, so you still have the Ivrea gravity, positive gravity anomaly, and you can follow nicely the European Moho here, but it sort of stops somewhere here at about, I say, 55, maybe. I'm not sure we can interpret that because we are in the noisy part of the Po basin. And we also have the VS section, which shows that the Moho doesn't go that deep along this section than along this one. And along this section is also the one where we had the Ecorse crop active seismic experiment. And if you compare the line drawing, the migrated line drawing that I showed you at the very beginning, with the receiver functions and with the VS section, well, they sort of fit quite nicely. And another message that I would like to give is, in fact, when you compare different types of a seismic image, a seismic tomography, as Andrew Curtis said, you never know if it's the right one or not, or if it corresponds to the real world. But when you have so different types of seismic data that sort of fit quite nicely, including the Moho depths, well, you feel more confident about your seismic image. Here, this is a comparison of those two sections, showing, well, the geological section, the receiver function images, the VS sections here, and the VP section from local earthquake tomography. And you in particular, if you look at these one, which are the VS section, they are very different. So in the south, you have European moho going very deep to maybe, 75 or 80 kilometers, while in the north, it stopped at something like 60 kilometers. So the Ecoscrop section was right. In the north, the subduction is not that deep as in the south. And of course, as the tomographies, we have a 3D VS model. Now we can make a map of a Mo proxy, which is here the 4.3 kilometer per second VS iso velocity contour. And while it's a good Moho proxy for Europe, not for Adria, because on top of the Adriatic Moho, you have serpentines, which has lower velocities. But indeed, you can see that yet you have enormous changes when you go from the north here to the south here, that you can also see on these short profiles on both sides of Cipher Alps 2. This one is in the north. This is the CCP section. So it shows a sort of a gently dipping moho, whereas this one, which is only 20 kilometers away in the south, has a the moho is dipping a lot more, as you can see on the VS section. So you have enormous lateral change within a few tens of kilometers or kilometers. You have really enormous change. So you have very striking and important along strike changes in the moho shape. And you can again see that here on these different cross sections all along the Western Alps. Across the Mercantour Massif, you still see the subduction. Here, Cipher Alps, you have already seen it, you see the subduction, but you start not to see it here. And when you go further to the north in Switzerland, you see the two mohos are almost flat. Okay, and so that's something which is a work in progress. We are, in this day, trying to build a 3D geological model of the Western Alps, which is constrained by seismic tomographies, just making cross-sections, discussing them with the geologists that interpret them, and put that in a 3D geomodel to see the geology of the Alps in 3D. Okay, and just I end on other stuff. We also make use of the cross-correlation data sets from Alperae and Cipher Alps. That was the work of Dorian Sorgel in his thesis, to extract CODA-Q information from the CODA waves of noise correlation in the 2.5 20 seconds period band, and that's the map of CODA-Q at 2.5 to 5 seconds in the Alps. We also did, Chloé Alder, who was a PhD student in Lyon, measured radial anisotropy from Bayesian inversion of ambient noise data, love and Rayleigh, so using all the three components of the correlograms, in fact. And we have, these are maps at 8 and 32 kilometers. Here it's a map of dV SV, so that's isotropic SV wave velocity. Here you have a map of radial anisotropy, and it's red when the SH wave velocity is smaller than the SV, and blue when the SH is larger than the SV. And you can see here that at 8 kilometers there is almost no radial anisotropy, whereas you start to see quite strong positive radial anisotropy in all along the Apennines here, mostly. So we are looking for anisotropy in the Alps, but we found some in the Apennines with a rather high probability. And I end up with Bayesian analysis of azimuthal anisotropy that Dorian also did in the last part of his PhD and the first part of his postdoc. That the paper that is submitted. He measured azimuthal anisotropy by beamforming ambient noise cross correlations fit the data as a function of azimuth by this formula here, and estimated azimuthal anisotropy. So these are the axes of fast velocities as a function of period, 15, 30, 40 seconds. And then he did a Bayesian inversion for depth variations, and the message of that is that you really cannot figure out what the azimuthal anisotropy is by only looking at the maps at constant period. You have to do the inversion, and you get quite unexpected results. Okay, so these are my conclusions. I will only focus on that one. Data in all that work is really the key. So you have to, well, either to take your part of recording data in places where there are not, and data opening is also very, very, very important. And the rest is the comparison combination of different types of seismic tomography helps deciphering the quality of your seismic tomographies. And of course, ambient noise tomography has a great potential, in particular for more depth estimates, but you have to go to rather long periods. And this is it. I thank you.